Okay, so now we're going to consider even and odd functions. Okay, now this isn't directly similar to even degree and odd degree functions, right? Because you can actually apply even and odd functions to functions outside polynomials. But these guys indicate there is a relationship between even and odd degree functions, which we'll talk about, but these guys represent or demonstrate lines of symmetry. Okay, so an even function, by definition, they contain a line of symmetry about the y-axis. Okay, so an example of an even function, I think the most common type of even function is a quadratic function, right? So this is my quadratic function. You can notice here that about the y-axis, this should be generally symmetrical. So I know I didn't draw this to scale, but this is y is equal to x squared. And along the y-axis here, I'm just going to highlight the y-axis. Right, along the y-axis, this line should create a line of symmetry. Okay, so all even functions have a line of symmetry about the y-axis, right? And I did highlight an even degree polynomial function, which I will talk about in a little bit. But let's take a look at odd functions. And odd functions, they contain a rotational line of symmetry about the origin. So what does a rotational line of symmetry mean? Well, if this is our function. Okay, let's say this is y is equal to x cubed. This is our function. A rotational line of symmetry about the origin means that there is this line that if you rotate it, right, you can understand that this is basically a plane. So imagine that this line is a plane, and these two halves are symmetrical, right? They're mirror images of each other, right? But if I rotate this line, and let's say that I move the line, let's say it's here now, right? And you can see that this half and this half are still mirror images, right? So if you keep rotating the line, right? If you keep rotating the line, you should see that you should still keep getting lines of symmetry. Okay, so that's what a rotational line of symmetry is, right? And you can test this algebraically. All even functions will satisfy this notation: f of negative x is equal to positive f of x. Okay, so this is something that you want to memorize. Okay, and this is how you can show a function is an even function algebraically. If you wanted to show an odd function algebraically, all odd functions will satisfy f of negative x is equal to negative f of x. Okay, so this is the tenet for all odd functions. Okay, so I'm going to demonstrate this using an example. Like, for instance, if the function f of x is equal to x cubed plus 5x, right? You want to test to see if it's an even function or odd function. Another quick way we can tell is if we're considering polynomial functions. What you need to remember is that all even functions are even degree polynomial functions, and vice versa, that all odd functions are odd degree polynomial functions. Okay, just having these rules in the back of our mind, we can understand that we know that this all even functions have to be even degree polynomial functions. This is not an even degree polynomial function, so we would do the test for odd functions, right? So the test for an odd function here is f of negative x should equal negative f of x. Well, I'm going to first test out f of negative x here. F of negative x is I plug in negative x for wherever I see x. In this case, negative x cubed is negative x cubed, right? Because if you multiply negative x by itself 3 times, there should be a negative on the outside, minus 5x. Now the next thing I want to test here is negative f of x, which is basically negative applied to the outside of this function, negative x cubed plus 5x, which is basically negative x cubed minus 5x. You can see that these two here, right, these two here are the same, right? So therefore you can say that f of negative x is equal to negative f of x, and f of x is an odd function. Okay, so that's the test algebraically, right? Let's take a look at another example. Now let's consider f of x is equal to 2x to the power 4 minus x squared, and do f of negative x here, right? And in this case you have 2 to the power negative x to the power 4 minus negative x squared. Now you can understand that the degree here is 4, so this is an even degree polynomial function, right? So this is an even degree polynomial function, so because it's an even degree polynomial function, we only understand that even functions have to be even degree polynomial functions. So I'm going to first test out f of negative x, but we recall that an even function, f of negative x, should be equal to f of x. Okay, so this was the tenet for an even function. So f of negative x here is 2 negative x to the power 4 here is x to the power 4 minus negative x squared is x squared, right? And you can see that f of negative x here is equal to f of x. Right, so therefore f of x is an even function. Okay. Now there are cases where both of those tenets don't exist, right? If f of negative x is not equal to f of x, or f of negative x is not equal to negative f of x, then we say that the function is neither. And neither just means that it does not contain a line of symmetry. Okay, so it doesn't contain a line of symmetry is the idea. Okay, an example of this, let's say f of x is equal to 5x cubed plus 2x squared minus 4x plus 1, right? And you would think that because the degree here is 3, you think this is an odd degree polynomial function, right? It's an odd degree polynomial function, so you could do the test. If you want to test to see if it's an odd function, f of negative x should equal negative f of x, right? If I plug in f of negative x here, you get 5 times negative x cubed plus 2 times negative x squared minus 4 times negative x plus 1, and you can see here that you get negative x cubed is negative x cubed, minus 5 times negative x cubed plus 2 times x squared, because the negatives would cancel out, plus 4x plus 1, and negative f of x here is basically negative 5x cubed plus 2x squared minus 4x plus 1, and if I expand this guy out, you get negative 5x cubed minus 2x squared plus 4x minus 1. And you can notice here that negative f of x, right, therefore f of negative x is not equal to negative f of x, right? And this was the test for an odd function. We can see here that, right, this would not be an even function because it doesn't have an even degree, right? So this is neither. So it doesn't have a line of symmetry is the idea. Okay, so even and odd functions are just associated with symmetry. In the case of polynomial functions, however, all even functions have even degrees, and all odd functions have odd degrees, right? However, that is not to say that all odd degree functions are odd functions, and not all even degree functions are even functions. So we saw that here, right, this was an odd degree function, but not an odd function. Right, so although even functions all have even degrees in terms of polynomials, and odd functions have odd degrees in terms of polynomials, the opposite isn't true, right? That odd degree functions aren't always odd functions, and even degree functions are not always even functions, right? So that's also a very important characteristic to understand as well.